Yang-Lee feature, which are responsible for the non-elasticity of the free energy. In the thermodynamic limit, these zeros, they pinch or cross the real axis of some of the parameters of the free energy. And when that happens, a non-analytical behavior rises. And that we call a phase transition. We did a simple model, the 1D ICE model for that, and there was a question about what would be the other parameter of this transition. Actually, we don't need that information, but we can inquire, and I gave a simple mind answer saying that's the density between, the density difference between the two states, the states that, remember, these are the hydrogens, so meaning that the arrows are to the left, the hydrogens near to the other oxygen, the arrows are to the right, and these are the circular configuration, counterclockwise and clockwise. So we could also imagine being the center of mass of the protons being the other parameter, because in the low T phase, the center of mass, remember we have two configurations, equivalent configurations. It will be either left or right, so there will be finite values. But at the high T phase, the X position of the center of mass is 0, so it's 0 above T. So you could think this as one of a possible other parameter. What matters for us is that we have the partition function. It can compute all observables and all singularities because we know where are the zeros. If you know where are the zeros, especially the distribution of zeros when it's pinching or touching or crossing the real axis of some parameter, then you know the singularity. As I told you, you have just to do some simple tricks like integration by residues or something like that. Yes, that's correct. Yes, I think it's a matter of semantics, right? It's you have a discrete set of zeros because your system is finite, and you have something like this. Is it crossing, touching, or what? So when we did our example, we discovered that the zeros, the imaginary part of the zeros is I, then there is a constant term here, divided by L, where L is the size of the system, and times N. And N minus 1 is here, plus 1 is there, the 0 you didn't have, they were equally spaced in the imaginary part. So is it touching, crossing, pitching? I think it's a matter of semantics. Yes, that's correct. Mm-hmm. Yes, that's why we need the thermodynamic limit. Because only the thermodynamic will have an infinite set. Well, actually, a cosine has an infinite set of zeros. But we have a set of zeros that are arbitrarily close to each other. So we would have a continuous of zeros. That's the point. Usually, it's hard to compute these zeros. And I mentioned that I only know this first order example that I told here, but Andrea was very kind to me to remind me that, well, actually Yang-Lee, they compute the zeros for the easy model, which is an integrable model. So usually when the model is integrable, we can compute Z Usually, let's not say, sometimes we can compute Z for all size of the system. Okay. Thanks, Andrea, for that. Then we talk about continuous transitions, where we have scaling variance, meaning that we have fluctuations of all possible size, meaning a correlation length diverging. And we have universality, that the transition undergoing, that the system is undergoing, doesn't matter of the microscopic details of the system. For instance, if you have a paramagnet, ferromagnet transition, does it matter if it's iron, nickel, or some other material? The singular part of the transition doesn't care about it. Of course, the transition temperature depends if it's iron or nickel, because it depends on the exchange, it depends on microscopic details of the model. If it's a liquid gas transition, does it matter if it's water, glycerin, or CO2 that I showed in the example there? Doesn't matter. So that's what I mean by universality. Okay, now we introduce disorder to this game. What I mean by disorder, I mean impurities, vacancies, dislocations, all sorts of things that somewhat removes the system from being a homogeneous or some regular one. You can have speckles in cold atoms, as Fernando, I don't know, Fernando was showing yesterday in that experiment where Anderson localization was seen. So all kinds of these non-regular pattern in space and also in time. So this leads us to a classification of disorder according to its dynamics. It is called quenched when the degrees of freedom of disorder is static in time, it's frozen in time, and annealed when the degrees of freedom, the disorder degrees of freedom, like impurity, they can move around, dislocations can move around. Usually happens in liquids and things like that. So if they move, they can equilibrate with the system, become part of a large system. So usually a new disorder doesn't only have mild effects, doesn't have strong effects on the dynamics. But there are counterexamples. I'm not going through that. But the quenched disorder, I think it's clear that it has more chance or more potential to do more dramatic effects, and that's the topic of this class. How you deal with disorder? As you want to compute the partition function of the free energy, how do you do? This is a very hard problem, even if the system is integrable. Because disorder usually breaks translational symmetry or other symmetries. And as physicists, we love symmetries, because then you can do some trick here or there, conserved quantities. Symmetries is related to conserved quantities. We can do Fourier transform, for instance. But when disorder is in the game, forget it. So people, the first approach, they were trying to do what is called replica trick. They use this mathematical identity. So you have to, in our case, you have to compute the partition function to the power n. It's already hard to compute the partition function to power 1. And now you have to compute to power n. But how do you do that in practice? Then you replicate the system. Let's say that you have any copies of your system. And somehow you average over disorder. Because this average here can usually be done easily if the degrees of freedom are Gaussian distributed. And after you do the average of disorder, then you compute partition function. Because now you come back to a clean system since you average out disorder. And average out disorder, statistically, the system is clean. So you recover your translational symmetry. But now you have a different system, which is somehow any copies of the original system average out. Disorder average out. Okay, I have any copies, 1, 2, 3, whatever. So I have to know this number to power n, and I have to take n to 0 now. So I have any copies, but actually you do n equals 0. So this procedure can be done. It's called analytical continuation. And there are some examples in the literature where these analytical continuations you define and you cannot do that. And it leads you to wrong results. But that's not the only thing that can be done with disorder. There are other things that I will present today and tomorrow and the day after tomorrow. Okay. Questions so far? Fernando, I suppose this is yours. Yes? Yeah, physically it can be complicated. It can be due to some replica symmetry breaking. So you have to do replica symmetry breaking, and this leads to some breakthroughs in the disorder system, actually leads to the Nobel Prize for Parisi. And sometimes the physics itself, that's one reason that you could fix doing replica symmetry break. So that's not a problem. But in other cases, it turns out the following. When you do this Gaussian integral here, you were saying that disorder can be well represented by average and the width. So there will be, after you do the average over disorder, you have a new system that has any copies of each system and has 2 more parameters, an average value and a width. Usually you take the average value to 0 and get only the width. So you get a system that has this parameter, and which somehow parameterize the strength of disorder, because larger the width, larger disorder. And sometimes the physics, the corrective physics, is that of this width being infinite. And if that's the case, forget about it. You cannot average disorder, because if disorder goes to infinite, it cannot be represented by a number. It has to be represented by its distribution, and the mean value of observables are very different from typical value of observables, and you need a different approach. So that's the reason, one of the reasons that this can fail. So there is a physical reason for that, yes. Yes, I have to take the average here, right, outside. But then you average the C to D, so you put the yes, yes. Yeah, that's related to this question, right? Because your average Z, not log Z. So if the physics of the system is intrinsically disorder, what we are doing here is practically trying to make an average, and not here. These would lead us. The thing is, if you want to compute an observable, do you compute the observable without average Z or after average Z? When you do the experiments, you're not averaging over Z. You have a single sample. You're doing the observable, so you don't average. But here in this trick, you are average over Z. Then after we average, we do differentiations like magnetization is differentiation of log Z or some differentiation of F. And then that's what you're saying, that's observable. So these two others these two operations do not commute in this case. So the reason why it did not commute, again, is because disorder, the physics is intrinsically disorder. Disorder is infinite, actually. Okay, so it's the same answer for, okay, thanks for pointing that out. All right, so another way, another classification of disorder according to symmetries. And I think this classification here is pretty useful because we can have what we call random TC disorder, or sometimes it's called random S. And we can also have random fields. Random axes, random phases, and random something else that we can come up with. In this, what is random TC? So I will try to make random TC. Let me draw this Hamiltonian here. So if I have random couplings or vacancies, I didn't put here, but we can have a chemical impurity near two magnetic atoms, and they would distort the orbitals, and this number here will be different when the impurity is there or not. So this is random. We call these random couplings for obvious reasons, and these random fields. So it's clear that this leads to random fields. And SI are easy variables, plus minus 1. But this guy here, it leads to this other sort of randomness that I'm classifying as random TC or random S. Why is that? Because suppose that the system is pure, J. This is only J, and then we know what's TC, I don't know, 10 Kelvin. If now I make this thing random, I have a larger, sometimes larger couplings, sometimes lower couplings. And lower couplings says that the transition can happen before 10 Kelvin, 9 Kelvin, 8 Kelvin or so. And large couplings, the transition would be a bit higher, 11, 12 Kelvin, and so on. So that's what we call random TC. But that's just a name. What has to do with symmetries, right? These degrees of freedom, these other degrees of freedom, it does not break the symmetry of the system or the transition. This transition, we argued yesterday, it breaks up and down symmetry between the spins, and being a random number doesn't matter if it's up or down. So if you put this type of disorder, the ferromagnetic state doesn't care if it's up or down, and neither the paramagnetic state. But this one is different. Because if B is positive, it wants up. If B is negative, it wants down. So this type of disorder, it couples with the other parameter while this type of disorder does not couple with the other parameter. So I'm talking about the other parameter and coupling to other parameter. Well, what does that mean? So for that, we need some field theory. And field theory, now I can say that field theory is useful. And let's see how. So again, we start with this Hamiltonian here. And I will do the following as Joey was showing in the exercise yesterday. So you need to do the following. Si is mi plus delta si. Let's just now recast Si not as being plus minus 1, but the average value of many spins over some region. So it's a continuous number, which has an average and a fluctuation. So Mi is simply the average value of Si. Okay? And as a simplification, I say that Mi is just M. And then we write these Si, Sj as Mi plus delta Si that multiplies Mj plus delta, sorry, just M because now I have and this is M square plus M delta Si plus delta Sj plus order of delta S square, which we're going to throw out. All right. Now I rewrite this delta as the usual. Delta is S minus M. And M is some mean value, it's a constant. So Si, Sj is approximately what you're going to have when I put Si, delta Si, Si minus M. I get Si here, get Sj here. I get 2 times M, negative. With this M is minus M square, so minus M square plus M Si plus Sj. And if you plug it back here again, and here I'm summing only over these neighbors, the final Hamiltonian is the following. So if you plug it back, and you probably have done that yesterday in the exercise, you get this. You get a constant term here. Actually, it's not constant because it depends on the magnetization. And a term that looks like an effective field over a single spin. The thing is, when I throw out these fluctuations, I'm throwing out basically the interaction. Not completely, because there is an effective interaction coming from the molecular field. So if magnetization is finite, that spins at site I is seeing the magnetization of the surrounding spins. And that's what happens. And Z is the coordination number. It depends on the lattice. If it's 2D lattice, there is one above, down, left, right, so Z is 4. Yeah, I'll come back to the disorder. So if I have that, I can compute now the free energy. And MF is mean field. So I can compute the partition function at the mean field level, which is actually a single spin problem, right? I have a collection of non-interacting spins to the power n, and is the total number of spins, and this leads to 2 times exponential of minus beta jz. So this is, okay, m squared divided by 2, hyperbolic. To the power n, and then we can compute the free energy. All right. But as Joey was saying yesterday, what's the value of m here? So m has to be such that it minimizes the free energy. There is another interpretation for this minimization, is that, well, I'm computing the Helmholtz free energy, which does not depend on m. But I just wrote it that it depends. So how come? Because the Helmholtz free energy depends on temperature and the external field, not on the magnetization. So you need to do some self-consistency, meaning that if you derivate the free energy by the external field, you get the magnetization. So you get magnetization from the left side, and from the right side, you match these two. And this is equivalent to minimize the value of F. So now, minimize F. I can plot this, how is this equation here. But it's not much of a use for us. What I'm going to do is the following. Since I'm trying to describe a continuous phase transition, around, near this critical point, magnetization is small. So I will Taylor expand this function as a function of m. And I will also say that the external field that I will put is a very small field because I don't want to perturb the system too much. So m is much less than 1, and beta b is much less than 1 as well. So I will be interested in temperatures near the critical temperatures, so this field doesn't remove you out of that critical region too much. So if you do this, And if you know how to do Taylor expand, it's just a simple algebra. I will not do that here. What happens is the following. Over Jz is approximate. And as Joey was telling you yesterday, you have a constant around the transition temperature. Beta is around the beta critical, so this is more or less a constant. You have a m squared term if b is 0, and you have a m4 term because b is 0. This guy goes to 0. And why it goes to 0, as Joey said yesterday, identically 0, is because symmetry must be respected. When B is 0, the Z2 symmetry is respected. And therefore, positive magnetization, negative magnetization are the same. So the free energy has to respect that symmetry. So you can say that it is a constant. Minus HM, or I suppose in my notation I put HM, which is external field, and this is plus 1/2 R m squared plus 1/4 U m4 plus blah, 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 and the m cubed term I put here as well. You can keep down and then write all the other. Okay. So you can see that, as Joey was saying yesterday, when R is positive, the minimum is m equals 0. When R is negative, you have 2 minima. And R is exactly this number. So Jz is Tc, right? Because beta is 1 over T, Kb is 1 here. So being T here, and the T greater than Jz, this number R is positive. So the minimum value is 0. When T is smaller than Jz, this is 1 minus a number that's bigger than 1. This is negative. Then you get, and then you can compute. Then you see that for R negative, you get a finite value of m. For R positive, you get a 0 value of m. This is already an analyticity, and that's where it's coming from. Coming from a minimization procedure. Because of B. B breaks the symmetry of the system. So positive M has different energy from negative M. And H is beta B, right? Okay, so that's the free energy if you did the mean field approximation. That is this one here. But if you had kept the dependency on position in the field M, you wouldn't have what we had here. What you would have is something different. That is Then that term that I wrote here, let's say Mi delta Sj. So Sj, delta Sj is Sj minus Mj, so I would have Mi Mj and have Mi Sj. So it had some things like some terms like that. Mj Si. Then you could say that this is Mri plus delta J. And here you get Sj. And then you will Taylor expand as Mr plus some constant that depends on the M plus psi square plus of M plus blah, blah, blah. Higher terms in Taylor expansion, Sj. And now you come back to your free energy, and what we would have is F over Jz would be approximately integral in space of a constant plus H or minus H Mr plus R over 2 M over R plus 1/2 xi naught gradient of M to the square plus U M of R plus blah, blah, blah. And that's your field theory. Wow, so much, right? And now come back to Rafael's question. Let's put this order again. So where this order enters here? Well, this H term here doesn't have any of the J's. By symmetry, right? Because the J's doesn't couple directly to M. So this guy here doesn't depend on the random J's. But it depends on the random fields. If I had put beta, external field, as a function that depends on space, then this would be a function that depends on space. But this is random field. And J enters here. So I would have a J as a function of R. And so this R would depend on R. Depend on the position. So that's why we call that random TC. In field theory, quantum field theory, this term is the mass term. It's M square here. We missed the square. This is the mass term, so sometimes it's also called random mass. And of course, you would have this psi naught would also depend on R, and this U also depend on R. But the U will be, it depends on R, but it will be positive, right? Because this is a positive number. This will be positive. And to ensure that the free energy has a minimum. All right, yes, many, okay. Because we know that these, in the randomization group sense, this is irrelevant when compared to that. You can also think as when M is small, this guy wins, right, through that. So this is a term that breaks the symmetry. This breaks the same symmetry, but this is stronger when M is small. So you keep this one. So you'd say, oh, why not throw out this one? Okay, you have to keep this one. And I could only keep these 3 here. And that's true if R is positive, because then I ensure a minimum. You can do your field theory with only these 3 here. And many of the observables, these 3 here is enough. But when R is negative, then you need to add this one here, so ensure the minimum. For some theories, this number here, U, is negative. Then you have to go to the 6th term. This is called tricritical points and so on. All right. Thanks for this question. This term that's proportional to M is not here anymore, right? Is Xi not here? Yeah, but remember, this. I have to go through this step again, right? I get this S, and then I compute, and I get something that is very messy here. But yeah. And this term is single derivative EM. Why did not appear there? Well, because since you interact in that direction, you also interact in the other direction, so it cancels out. It's more or less because of that. Even if you hook up with some fancy lattice, you have to average over a large region, and then it averages out to 0. Yeah, the dimension is specified here, right? So it's there. Yes, it is. The first step is mean field, so you remove the gradients and do as was in the exercise yesterday. Now, if you want to do a better job, you have to keep those gradient terms and do some perturbation theory. So there are diagrammatic expansions, Feynman diagrams. You can do many things. But even if the mean field in throwing out these gradients is not enough to capture correlation functions. So I told you that the correlation length, I drew right here, is infinite. So to compute correlation functions, we need the gradient. We need this term here. And you can do this term is quadratic, so you can do what is called Gaussian integration and compute the correlation function. And then you see that Xi really diverges to compute all critical exponents. So this is a nice exercise for mean field theory, phase transitions that you probably have done in some course, I don't know. All right. Questions? All right, if not, we have classified our types of disorder, right? Random mass, random field, random access. In this case, if my model had a larger system like a spin 1 system or higher spin system, then you could have, and they would have Heisenberg symmetry, you could have a preferential access that the spins wants to align. Then another term would appear here. These would not be scalar numbers. These would be vectors, or if you have a different sort of transition, then you could have different sort of objects here, like tensors and so on. So this, You can describe lots of systems with this approach. That's why field theory is so successful, so appealing. You can, after writing down the field theory, you can do perturbation theory and compute observables. All right. So I will change a little bit gears now and pose the following question, actually. A simple question. We did all this stuff here, but can we answer some question instead of dealing with that, some simple questions? And the question is the following. Suppose you have a system undergoes a transition. Oh, these remind me that I didn't tell you something yesterday. Change the phase of the matter doesn't mean that there is a phase transition. Somewhat here. We could go from the vapor phase. Where is this stuff? Well, let's go back to the old-fashioned one, which is here. I could go through the vapor phase, crossing the transition. What's the transition? We define a transition as a non-analyticity. So this is a kink here. This is a non-analyticity. We could go from here to here through the transition, through the phase transition. But we could change the phase from vapor to liquid in this way here. So I could go from vapor to liquid, and there is no non-analyticity being crossed. So I changed the phase, but I did not have a transition. Somewhat fancy, right? But this can happen. I will not say that.
There is only a fluid phase which we happen to call vapor or liquid because it's important to us to make that distinction.
Yeah, okay, but for practical purpose, liquid has very different properties from vapors, and you can say that there are different phases of thermodynamic phase. Yeah, okay. A state of matter that has some given properties, and I have a property in this one that are not in this one, right? Like compressibility. Well, compressibility here is practically infinite for some practical purpose, and here is finite. Okay, you can say, well, I can still compress some fluid. Yes, that's true. And if you admit that, then you're right. Then this phase is not different from that phase. And the same thing as this phase is not different from that phase. Okay, so if that is the case, this leads me to the next statement, that if different phase of matter has different symmetries, or from one phase to another, you has to break a symmetry, then you cannot do this path here. So I could not go from solid here to vapor without passing through the kink. There is a kink here, there is a kink there. I cannot go from here to there without crossing the kink in the state equation. There is a critical temperature because there is a non-analyticity at this point. You are just touching the tip of the kink here. So that's Well, here, every point here, there is a region around where the properties of the system or your partition function is analytic. So there is a finite any point here there is a finite region where if you Taylor expand around it, the radius of convergence of the series is guaranteed. But not at this point here. Because if I Taylor expand through this point, well, I'm already in the tip. So if I go to the left, it's different from going to the right. There's a kink there. Okay, thanks for the discussion. Okay, so suppose a system undergoes a phase transition. Then we can ask, or do the phase remain, or do the phase change? Like this transition here. If I diminish temperature, then to the left of TC, I have a magnetic phase. To the right of TC, I have a paramagnetic phase. So if I introduce this order, does this phase survive? Because the phase could change, or the transition could be destroyed. But I'm supposing that, yeah, that's another question that I have to do. And do the change, if the transition survive, do the phase change? If the phase doesn't change, let's say it undergoing a continuous transition, do the critical behavior change? Or does? Remember, we are talking about universality, and let's say that we put random J's here, random mass. And it looks like small details, right? Do these details matter or not? If the behavior is universal, it shouldn't matter. But we can answer this question in a very simple way. This is the so-called Harris. This is not good. And the Harris criteria is so important that I cannot draw there. I have to put in the middle of the blackboard. So I'm kidding. I go there. So Harris has the following idea. It's a very simple idea. Actually, was in the appendix of his paper. I think he didn't give much of attention to that, but later it was realized to be a great thing. And it was the following. Here is your sample. And then you divide your sample in blocks. Blocks of size xi. Just a length scale that you can choose. And then he made the following question. We have random couplings around, right? Let's say that we are considering random mass. We know that the random mass doesn't change the phase. Remember, ferromagnetic, up or down, doesn't matter. The couplings will not care about it. It respects the symmetry. So I have random couplings here. And suppose that here random couplings by chance are greater than average. So if the system would be put to infinite like that, we'd have a TC that is high. So let's call this TC1. And here, suppose the couplings by chance are weak, would have a low TC. Let's call TC2 and so on. TC3 and so on. If I would draw the histogram of TCs, how would that be? And I will not draw the TC, I will draw the histogram of something very close, TI, that is 1 minus T over TCI. This is called distance from criticality. So suppose now I'm in the disorder phase, very high temperature. So actually it's the other way around, TCI over T. Very high temperature, so T, all T's are positive. But they are not equal, because we just said that, right? So there will be a distribution like this. There will be an average T, and there will be a width, delta T, right? Just because system is disorder. And here is the transition, right? 0, when T equal TC. Then Harris put the following question. If I diminish the temperature, I diminish the average T, but what happens with this width? Does it becomes broader or sharpen? That's the question he posed. So now I diminish temperature, and does this become like this, or this becomes like that? Sorry, that's the question. So how do we answer this question? Can you think about that? I would like to hear your ideas. And he will use, let's be a little bit more, give more information. What means diminishing temperature? Well, I'm diminishing T, so the distribution is definitely going to the left. If I diminish T, I'm certainly closer to the transition. If I'm close to the transition, this correlation length increases, right? So this is high T. Well, this is psi, but then when I go from here to here, psi is now this big. So instead of having T, 5, 6, 7, 8, I'll have a single T. So I have to average over all J's around here. Remember, the average J here is high, so TC is high. Average J here is low, so low TC. And now I have to average over a larger block. So if I have to average over a larger block, what do you think that happens to the width? This is the central limit theorem. Sorry, it's positive, right? So what happens to T when we lower it? Well, it diminishes. But it'd be nice to connect with Xi. But remember, the clean physics has the following property. At the clean critical point, we know that this is 1 over T to nu. When T goes to 0, Xi diverges. So actually, if I have a T average, I would have this as, oh no, this is negative. I put in 1 minus a number. This number can never be bigger than 1. So this has to diminish. So Xi is, T is Xi to minus 1 over nu. So this symbol, you know what means this symbol, right? It just behaves as, goes as, so this is Xi 1 over nu minus D over 2. And if we want this distribution, if we want that, if we require that the clean critical exponents be the correct one, meaning that the clean theory be the correct one, this distribution has to become a delta Dirac when I undergo the transition. Because I cannot, in conscious mind, say that a clean system undergoes a transition like that. That a part of the system underwent the transition and part did not. This is not compatible with the clean theory. So, see, going to infinite, what do we have? If I want this to go to 0, when T goes to 0 and Xi goes to infinite, what's the requirement that I need? I need that 1 nu minus D over 2 be less than 0. So when psi goes to infinite, this thing here goes to 0, so meaning that this ratio goes to 0, this is a delta Dirac. So this means that I put D to this place here, and this is D larger than nu over 2. If I put there, the nu larger than 2. So what the Harris criterion is saying, that if we want a system to be stable against the introduction of random mass disorder, d nu has to be greater than 2. And this is a necessary condition, not a sufficient condition. Necessary condition for the stability of the clean system. If this is violated, then we know that disorder is relevant. So you have your system that you like a lot. You have a model, and you compute nu, you compute D. It's easy to compute D, right? And then you go to the lab and see, I want my theory to be confronted against experiments. And the experimentalist will build a sample, do the measurements, and he will say that the critical exponent that he measured does not match with yours. Then you're going to say, oh, maybe my model is wrong. Well, that's a possibility. But if d nu is less than 2, maybe your model is correct, but the sample has impurities or some sort of random mass disorder. And if that's the case, you shouldn't measure the clean critical exponent. You should measure a different set of critical exponents because disorder is relevant and will change the critical behavior. So that's Mr. Harris up there. And for this appendix in this Journal of Physics in '74, he was awarded the 2007 Laszlo Saga Prize. Okay. Questions? Yes, these T's here. I'm average over the disorder variables, and you should ask about, not should ask about, but what you have to think on the following way. Are the disorder variables correlated in these length scales? I assumed here there is no correlation between the disorder variables, so that's why I use the central limit theorem. That's an assumption that you have to make. If your disorder variables are correlated over some length scales or something like that, then you have to change this part here of the calculation, and that's what Joey will tell you in the next set of homework. Everything matches here, see? But if they are uncorrelated, you can grow this thing here because the random variables here doesn't care about each other, because that's my assumption. And fluctuations over here has nothing to do with the fluctuations over there because they are farther away than the correlation length. So everything that we are doing here is consistent in this way. All right, further questions? Yes. Yes, Mm-hmm. Yes, all these sort of correlated disorder or disorder that are distributed with some tails, you have to be very careful how to use the central limit theorem. So if you have a fat tail in your distribution, then you can change this exponent here, and Joey will say how it changed. Actually, I can tell you the difference is the minimum of D and A is the power law of this fat tail, if you wish. But you have to be very careful because what I'm doing here is TC disorder. So the disorder that you put, it can have some fat tails, but you have to be very careful. You have to see how it couples to the random mass term. So sometimes just putting J's with some distribution is not the J that appear here. So there is some small details. We have a specialist here, Andre, that works with aperiodic systems, and it's not simple how to compute this, how these other couples here. Because it's actually the distribution of R. I'm saying TC here, but it's actually, I should put R1. Actually, that's R1 I erased, right? But this was JZ over T, beta JZ. 1 minus beta JZ over T. So I have to see how it couples. All right. Further questions? Yeah. It's for, let's say, if this is violated, disorder is relevant. If this is not violated, maybe due to the normalization of other things happening, you could still have some other things that in the clean theory would not be respected. That's one thing that has to be respected in a clean theory. You need the delta Dirac here. But maybe there is something else that I'm not thinking about that can happen. That's, there are some examples that this. In perturbative, yeah. Disorder is perturbatively relevant if this is violated.
Is it perturbatively irrelevant?
That's the statement that's not correct. I have a counterexamples, but it's very rare. You have to be very careful. Most of the case, in the general case, if this is respected, then disorder is perturbatively irrelevant. In the most case. There are some exceptions. All right. So if disorder is relevant, what happens? This criteria does not say what happens. The critical behavior certainly has to change. And the next lectures, I will give you a tool how to see, how to quantify this change in the critical behavior. So I have to do some heavy stuff for normalization group technique. But I hope you find it amusing. Okay, so this was for the random mass, right? And this was done in 74. So after that was done, it inspired other people. Oh, that's what is coming for. It inspired Mr. Joe Inri and what's the name of Shanken Ma to generalize this criterion to random field. So how is? Oh, it's already written there, right? So do I need to go to Blackboard? I think so. And the random field is very, very nice because it has even more dramatic effects than random mass. And I will show how it happened tomorrow. I will give a colloquium, and the random field will appear there, I promise you. So the idea was the following. Very, very simple idea. Actually, they were asking this question here. Do the transitions survive when disorder is introduced? In this case now, random field disorder. And the INRIMA criterion is a criterion for the survival of the phase transition. So the Hamiltonian, let's just consider, is the usual Ising Hamiltonian with some random fields. And this random field has 0 mean. It has to be 0 mean, all right? Otherwise, we don't have the transition. If the mean is not 0, you miss the transition, right? H is finite, you just go here, right? Because H is finite or here. It has to be at least 0 mean, so you hit the transition. Or hit the non-analyticity. But, so average is 0, but it has finite width. And let's call this width B square delta ij. So if I is different than j, this is 0, meaning that are uncorrelated random variables. So you can think of B and the probability of B as something like this. This is 0 mean, but this is, let's call it delta B. The probability of B. And I will do this delta B very small because I want to do, to see if its perturbativity is relevant or not. So I will go to t equals 0. So I know that I'm very low temperature, so forget about thermal fluctuations. I don't care about thermal fluctuations. And what those gentlemen thought. Suppose I'm at t equals 0, and I will assume that there is a ferromagnetic state. That's an assumption, and then I will reach a contradiction. So I'm at t equals 0, and there is a ferromagnetic state. All spins are up. So we know we compute this, the energy of this state. We get minus j for every pair, and you get Bs, which sometimes is positive, sometimes is negative. So sometimes you gain energy, sometimes you are counter-aligned with the field, you lose energy, right? And then they inquire, well, maybe I can come up with a better state. And the state is the following. It's this one here with a circle or a region around here. It's not exactly a circle. Some region around here of a size L, that everybody here is down state because mostly here the fields are negative. The fields are positive and negative, right, with equal probability. But sometimes you throw the dice or the coin and get many negatives instead of positive. So you could gain the energy by putting everybody down. So how much of energy you gain? I put a down domain here, so D is of domain. So that's the energy gain from the domain that I nucleate there. That is everybody below here. Okay? So how much is this gain that you win? If you average over this region around, the gain on average is 0. Because sometimes it's up, sometimes down. But of course, you're not going to do that. When you gain, you stuck there. But of course, not everybody here, because they are uncorrelated random variables, not everybody here is down. In most cases, they are down, but not much, not always. So you have to gain the energy from the fluctuations, from these fluctuations here around the mean. So if I increase the size L, how much these fluctuations, how do the fluctuation change with the size of L? When I sum here. I'm putting everybody down, so I'm just summing B. That's the energy gain, the sum of all B's inside this region. And how much this sum can be? Well, you have to fluctuate and fluctuate. And if I now ask what is the distribution of the sums of B, how is that? It's a Gaussian, again, central limit theorem is a Gaussian with what width? A width that grows with the square root of the number of B's that inside there. So that's your energy gain, the square root of the volume. But of course, you lose some energy. It's the domain wall energy, because here is up and here is down. So this is proportional to delta B. And the energy cost is the domain wall, because here in this, around this perimeter, I have an up spin and a down spin. So this is cost J. So this is J L to D minus 1, because it goes to the area with the area. The domain wall goes with the area. So now I have to compare who wins. So if the ferromagnetic state is stable, I cannot grow this domain here, because this domain has to be small, so most of the bulk is in the ferromagnetic case. So I have to compare delta ED with delta E domain wall. And this goes to L D over 2 minus D minus 1. That is L to 1 minus D over 2, right? So when D is less than 2, so if I want the ordered phase to survive, what do I need? This domain wall has to explode, right? When L goes to infinite. So this has to be larger than 2. So at the sufficient low dimensions, random field kills the order state. It kills the transition, meaning that DC minus the lower critical dimension of this problem is 2. Remember the lower critical dimension? I told yesterday, fluctuations are so strong that they even prevent the transition. So that's it for this problem. The random is in the longitudinal, random longitudinal field. But I didn't say about the equal to, right? I just put that 2 will not happen, and that's there is a rigorous proof that at D equal 2, you do not have another state as well. And this comes from, what is that? From Eisman-Ver, that PRL. that the D equal 2, also you do not have the other state. You can generalize that for other models, like for the Heisenberg model that has continuous symmetry. And when you have continuous symmetry, you can go from the up to down state slowly. So you do not pay much energy when rotating. You can show that when the symmetry is continuous, actually the domain wall cost is not the area, but d minus 2. And I get a d minus 2 here, and I get a 2 here, and this will be 4. So random fields in system that has continuous symmetry is even more dramatic. You shouldn't see in nature practically, because the lower critical dimension would be 4. So if you have a Heisenberg magnet and put random fields there, don't expect another state, unless you go to dimension larger than 4. All right, I have 1 minute left. And now ask, well, we are talking about the classical systems, right? How about quantum phase transitions that we talked yesterday? And also Joey put in the exercise how to do the classical quantum mapping. So if you remember correctly, how do a quantum system undergoing a quantum phase transition at 0 temperature? It can map in a D+1 system at finite temperature, classical system. How is that? You do copies of your system. Suppose that you have a 1D system. And let's suppose that we have random mass. So I have a random J here that is very strong, a weak J, a somewhat weaker J, and I don't know, some very strong bond. This is 1D. Then you have to replicate your system, right? This is the other direction that is called imaginary time direction. That comes from the Trotter-Suzuki trick. So you have to replicate it. And so on. And the vertical couplings, they are all the same because they are due to the thermal fluctuations, actually the quantum fluctuations, which somehow they mapped now to thermal fluctuations, and then there will be a unique J in the vertical direction. Now I have to compare this guy, which is a classical 2D model, with a classical 2D model, with random couplings. So if I 1, 2, 3, 4. 1, 2, 3, 4. Now I go to my easy model and put random couplings. So I have a strong one here, a strong one here, a weak here, somewhat strong here, somewhat strong there, somewhat weak here, and so on. And I don't know, something like that. Which one looks more random? The quantum one undergoing a quantum phase transition, or the classical one undergoing a classical phase transition? At first glance, you could say, well, this looks more random than that. Therefore, this order is more relevant here than there. It's not the case. It's the other way around. Why is the other way around? Remember that when we were doing the Harris criterion, we were average over a system of size psi, right? And I was averaging the couplings in this region here. So larger the region, smaller become the width of the distance from criticality. But how about here? If I increase this direction here, I have the same couplings. I have a J1, J1, J2, 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 and I keep increasing. I'm not diminishing the width because this order is correlated in this direction. Only when I expand in this direction is that now I put another J's and I average other J's, and then the width diminishes. So actually, what I should put here is D minus 1. So D is actually, what is the hierarchy? D is actually the number of dimensions where this order is uncorrelated. And in the quantum phase transition, the new dimension, D plus 1, let's say, in this plus 1 dimension, this order is correlated, perfect correlated. So it doesn't average out, so I still use D. So it's D. But why it's even relevant? Because D is less, right? The D in the quantum case is 1, while here is 2. So I have more chance to violate this, and this order has more chance to be relevant. Okay, maybe I'm putting too much information now. We need some time to process all of that. I think I'll stop here. And is there more questions? Well, if not the case, let's go to the coffee break. Thanks.